Okay, this is about where we were last time, right? We were kind of like showing, okay, how to set up everything. We basically register all of the modular things that we're going to pick, like crossover, mutation, how they're going to be done. They get registered to this toolbox thing. And we also talked about how, like, okay, well, mean squared error fitness. Yeah. What happens is, so here's mean squared error fitness. It's different from the mean squared error function, mean squared error fitness. The mean squared error fitness will take an individual of the toolbox, independent variables. It does some checks. But then it needs to take the individual and compile it. This basically means, okay, great, you've got this tree structure, this S expression, but I can't run it. This turns it into something that's actually runnable. So it converts it to like an actual function that can be run to get something out of, right? So we have to give it a callable function. Then we called mean squared error with the function that we can call and the variables. And then finally, and you'll notice that this returns a tuple. Remember how I showed you when setting up? If we go all the way back up here. Where was it? Maybe I went too high? Yeah. Remember here, the weights? It's going to have to match. So even if you have a single objective, where in this case we want to minimize mean squared error, it's got to be a tuple. Again, you asked, like, does it have to be a tuple or maybe some other iterable? I don't know. I always use a tuple. Put in parentheses, add a comma, it'll be a length 1 tuple. Great. And what gets returned by the fitness function is going to be a tuple matching what it is. So when it comes to actually like evaluating the fitness, those weights are going to come into play, but this just returns the fitness. Cool. And then bloat control. So when we were creating the S expressions, we would set some limits on like, okay, don't make trees that are too big, right? Big in terms of depth and the number of nodes. Well, we also can set some constraints for evolution when applying the genetic operators that like, well, you know, you really shouldn't be going bigger, like the max height should be set to be no bigger than whatever, and same with the number of nodes in the tree. This just helps reduce bloat. But herein lies a bit of a problem because you gotta recognize that I don't know if I set these limits too low, I might not be able to find the solution I need. Because what if the solutions that we're looking for are sufficiently complex to need like a depth 6 tree, for example, where this won't allow it? And this might sound like, well, yeah, obviously. We need to make sure our encoding can represent all good solutions. This is like going back to TSP, right? We want to constrain the search space as much as possible while still making sure our encoding can capture all valid, good solutions. Same thing goes here, but like it's got an infinite search space because like, I mean, the depth can go on forever, right? So like it's kind of hairy. But yeah, so you got to be careful. And remember, like if you're using GP, that means like, typically that means you don't know what you're looking for. You know what's good, but you don't know what you're looking for in a function, so how could you really know there? So this is just something you need to keep in mind, okay? Like if you're doing something that if you, like let's say you have like a 10 variable regression problem, and you want to, let's say a 10 variable regression problem, and you were to do linear regression. Well, if you do linear regression, you're going to get something that looks like this. Y hat equals like x1 beta 1, I think that's backwards, right? Isn't it beta that comes first? It doesn't really matter, but I'm pretty sure beta 1 x1 plus beta 2 x2 plus beta 10 x10 plus some constant, right? It's going to look like that. Now, consider what the tree would look like if we did that, right? We would need to have, so this is, if I were to do linear regression, I get this. If I do the basic math, I get this. But let's say our hypothesis is, oh, we could do better with symbolic regression. But imagine you set your limits such that your symbolic regression couldn't even build this if it wanted. Now, to be clear, the likelihood of symbolic regression getting something like this is hilariously low, but the fact remains, if we had it set up such that it couldn't even get this, we got a problem. Like, here's what I mean, right? Okay, we would have to have something like beta 1 x1 times plus beta 2 x2, right? Plus, right? You could start to see like, oh boy, how big is this tree going to be? If I set my depth limits and node limits too low, we're in trouble. So bloat is a problem, but don't get overly aggressive in trying to control it such that you really hamstring your search. And then here's some bookkeeping. There's a nice tool built in with DEAP called like Hall of Fame. You create a Hall of Fame object, and then you can say like, well, what statistics do I want to have? Well, I'm going to say that this is just a lambda function, an inline function for like saying like, okay, we'll get the fitness value of each thing. That's one of the statistics for the fitness. The size, like how big is each one? Len function on the tree structure to how many nodes there are. Height, we can get height as well. If you're looking at this and you're like, how would I know how to get, you wouldn't. You just look at the documentation and you figure it out. I want to get the height one as well. Multi-statistics, okay, and I set, okay, what are the three things I want to do? And what value, like what summary statistics do I want of these things? Well, average, standard deviation, min, max, because why not? Does it matter that I'm using average? It doesn't really matter. This is just for demonstration purposes. So yeah, the Hall of Fame. It's a nice little tool for keeping track of things. So to get this all set up, I create a population, toolbox population where the population size is specified. I use the algorithm from the algorithms library. I create an EA simple evolutionary algorithm. If you go to this library, if you look at this, there's going to be a lot of different options. This is like the simplest one, right? When doing like assignment 2, I would recommend don't just jump to look at what's available. There's a lot more interesting options available. We set a Hall of Fame, MStat. We just set all of these values, and if I hit run, I get something like this in the end. I have omitted rows 4 through 96 for brevity, but we would get something like this, right? So generation number, average, gen max, min. I'm not 100% sure what any vowels is here. I can't remember. Standard deviation. And this is for fitness. If we were to scroll, there's the same thing for the height. The same thing through the size, right? So the problem is, too, whenever you're doing like ASCII columns, you're going to be like, wait, the minimum tree size was 100? Well, no, that's standard deviation. We're kind of like off. Tabs, yeah, they're a hell of a thing. So be careful. But we can see, like, let's look here, fitness, okay? So the average fitness, we're minimizing, so max isn't great, min, whatever. Look at that, wow. It looks like we pretty early, yeah. No, I'm not sure. Why did we go up to 1? I don't know. Whatever. You can see that the average fitness definitely improves over time. Although, like, Must have done some changes that really hurt a few, I don't know. But neat, right? Height. You can see that I'm guessing this is average here. Look at that, the average height actually gets smaller over time. The number of nodes, I'm guessing it's this one. Yeah, also gets smaller. So anyways, you get some nice summary statistics in the end. Oh no. Yeah, cool. Now, one thing to note, and listen very carefully to me right now. Let me double check I'm recording. Okay, listen very carefully. If you go and you read the DEAP documentation, there will be, here, let's see if I can find it. DEAP Python. No, I want the actual docs. Okay. If you read here, give me a moment while I try to show you, like maybe if I go down to like GP, let's say there. No. No, come on. Maybe they may have actually removed it from, Yes, okay, cool. If you go through the documentation, you will find like, oh, hey, you can actually print these trees, right? There is a plotting trees, right? Good luck getting it working, all right? Although this looks new, and I'm actually curious.
It won't work the way the other tree works.
It won't?
It won't work as nice.
You tried?
I did.
Yeah, and it didn't work. Yeah, okay, so.
It was
Okay, all right. Did you get this one working? Where they look, in the end, they'll look something kind of like this?
No.
Okay, all right. So years ago, back in like 2020, through a lot of pain and suffering, I got it working on Linux. But I could never get it working on Windows, or vice versa. I can't remember. I'm pretty sure I got it working on Linux. And then a couple years went by, and I had to get it running again, and I couldn't get it working again. Crap. And then after a long time, I got it again. Got it working again. And then since then, I haven't been able to figure it out again. So, kind of lame. But here's why I wouldn't be too worried. So first of all, remember that the trees you generate are going to be weird looking, right? You're going to get things like I showed you, right? Where it was like x plus 1 ended up being some weird tree, if you remember I showed you, right? So you're going to plot those trees and it's going to look something like that and you're like, well, whatever, right? In the end, and I'm pretty sure it's probably on the website somewhere, but if you take, so Hall of Fame at 0, that'll be an individual, okay? The individuals are saved, all right? You could also do the same thing with like any individual in your population. You could do the same thing. But if you convert it to a string and then print it out, and you actually do explicitly need to convert it to a string, because I'm guessing repr and str are different as defined in that class. Not 100% sure. It's Python. But if you convert it to a string and then print it out, you will get something that looks like this. All right? Now, you're still left looking at that like, what? But that is an S expression. All right? That is an S expression that looks like, where did I put my marker? You just have to get, okay, so it's add arg1 to arg1. So plus 1, arg1, that's like x, all right? And then to that, we negated and then we negate it again. So if you simplify this, it's x plus 1. All right? There we go. That is what I got, and here's the mean squared error I got for it. All right, neat. Yeah. So you will still need to like manually go and clean up what you get. It's a required step for GP. You're only really allowed to get away with giving us dumps of crazy looking things when you're doing sufficiently complicated stuff where people go like, yeah, screw it, I don't know. It worked, great. Which then is kind of amusing because it kind of defeats the purpose, because one of the whole thing with genetic programming is like, oh, it generates symbolic functions in the end. You can look at them and understand them, but then once they get sufficiently complex, you still can't. You could in theory, but it's just, all right, so there we go. arg0, it's the only independent variable. I called it x, whatever. It's y equals x plus 1, right? Really, that should say y hat, right? But, yeah. To let you know, I almost certainly, I don't remember, but I almost certainly generated this with the function. Like I generated a CSV with the function x plus 1. Then you might wonder, well, why that? I add tiny bits of error to each one, right? To like simulate like, oh, it was recorded by some sensors. I don't know, right? It's never going to be perfect. Now, again, we talked about this before. Given the stochastic nature of the search and the fact that, like, you know, we talked about bloat and how there's more bigger programs that represent the same thing than there are smaller programs and all those funny things. All of these, and this is just a quick, when I generated this, I like took like the first 5 of a population of I don't even know how big. They all mean x plus 1, y equals x plus 1. But look at them, right? Now, we could simplify each one, right? Divide arg1 by the negation of itself and then subtract that from arg0, I guess. So let's look at that, right? So that means x minus x divided by negative x. All right? So, okay, what is that? Well, that's like x minus negative 1, x plus 1. Hey, right? This is what GP does. It's always kind of, sometimes it's really amusing, right? Like, look at this one, right? Like, oh, that plus 9 minus 8. Like, look at what's going on down here. This one's nuts. It just keeps going, right? But if we simplify it, it's going to be x plus 1. Any questions about what I just showed you? No? Okay, so we're not going to do this over multiple days, but just because I want to make sure you get a little bit familiar with DEAP and running it going into assignment 2, because assignment 2 is probably going to be the most complex assignment you do by virtue of having to interface with DEAP, all right? Assignment 3, by the way, warning, assignment 3 is particle swarm optimization, all right? And let me show you real quick. Source. So particle swarm optimization, if one really wanted to, not you, but if one really wanted to, you could use DEAP for a GA. You could use DEAP for PSO. Now, you're not allowed to, because that's overkill. DEAP makes sense for GP. PSO is hilariously simple, all right? And here's like, I will show it to you later, but like it's hilariously simple. Like look at that. Look, this is PSO, right? And all of this right here, this is just like the function we're optimizing. This is PSO. So it's a really simple algorithm, so don't use DEAP for PSO. If you go through the docs, you will find where's DEAP? examples. PSO, right? Like, you're going to find examples, right? But I feel like it's probably going to just be more complicated than just building it yourself, right? So do that. Not even build it yourself. Use what I gave you as like a starting point for assignment 3. But because assignment 2 is the trickiest, I'd say, because it requires interfacing with DEAP, we're going to then switch gears today, whip open your laptops or whatever you got, and try to get DEAP running. You're going to go through this experimenting with symbolic regression. If you go here, you will find 20 CSVs that all, I mean, some of them get sufficiently like more complex, right? I guess that's only like 3. What's this one? Is this one exciting? Look at that, crazy, yeah. And I want to see if you can get GP running and you tell me what the functions were. Each of these I generated with a function, all right? Your job is to tell me what function I used to generate those tables. So that's your job right now, okay? Cool? By all means, feel free to work together. It doesn't really matter to me. But we're going to switch gears and turn it into like the rest of today's lecture is more of like a lab. So you get a chance to make sure you can get this working so you're set up right for assignment 2. Any questions before I move on over? All right. What's up? Yeah, I mean, go ahead. Yeah. Okay. Yeah. Yeah. I mean, go. If you ask nicely, maybe someone will help you out.
Yeah, last time I tried, but it's not.
Okay. All right.